Okay, so today we will see some use of these one-shot quantities in areas outside of information theory proper. So today we'll see an application to an area in computer science, which is called communication complexity. That is broken. Complexity. Yeah. So have you heard or seen something about this area, Harikrishna?
Sorry, which area?
Communication complexity.
So not much, but yeah, I have an idea of like what it deals with.
You have an idea. Okay, so the model. So communication complexity is an area in theoretical computer science, and it was actually first proposed by Andrew Yao, a very famous computer scientist, way back in 1979. And his motivation for doing it was to prove lower bounds for circuit size for VLSI design. That was the original motivation. And since then, people have found connections to other areas. Typically, it is used to prove lower bounds for problems in simplified computing models. So you cannot prove lower bounds, any non-trivial lower bounds for running time or space complexity of problems for a general computer, but in restricted models of computations like limited types of circuits, okay, or a limited model of circuits that's used in VLSI design or something, we can prove some bounds. And often these bounds are proved using communication complexity. So the model that we will study today is the simplest model of communication complexity, which was actually considered by Yao in his original paper. So that's called the simultaneous message model. So in this model,
I can't see the screen.
oh, you can't see the screen. Oh, sorry. Where does share? Ah, oh, I think I just forgot to share the screen. Oh my God. Sorry about that. Okay. Now can you see it?
Yes.
Yeah. Anyway, so I mean, what will go up will be a cleaned up version of this with slides. This is just okay. So the model we are studying is communication complexity, and in particular, the simultaneous message model in communication complexity. So in this model, there is one party called the referee, and then there are two more parties. So this is Alice. This. Oh, okay. So the three parties here. One is called referee, then there's Alice, there's Bob. And the idea is as follows. So Alice gets an input X from some alphabet from the outside. Okay. So she doesn't pick it up, it comes from the outside. Then Bob gets an input Y from the outside. Okay. It comes in. Okay. Now, depending on the input X, Alice will send some message to the referee. Okay. So this message we call it's a function of X, M of X. And similarly, depending upon Bob's input, Bob sends a message, let us say NY, function of Y. Okay. And what is the purpose of this model? The purpose is to compute some function f of x comma y. Okay. So there is an underlying function which is to be computed. We'll see a very simple concrete example, which very soon, and that is what we'll keep studying in this lecture. So task is to compute f of x comma y. So as a simple example, let us say x, an input is supplied from the outside. Let's say it's a bit string of length n. Okay, so x is from 0, 1 to n. Then Bob also gets something from 0, 1 to the n. It's a bit string of length n. Okay. Right. And the function fxy. So let us say the function that we are talking of is the equality function. So EQ. So what is EQ of x comma y? Remember, x is a bit string of length n. Y is a bit string of length n. So this is the output of this function is either 0 or 1, false or true. So it is 1 if and only if x is equal to 1. So x equal to y means each of the n bits of x are equal to the corresponding bits of y, equality of bit strings. And it will output 0 if x is not equal to 1. Very bad. Without a proper writing time, this yeah. So is the model clear? So the aim is to compute some function f. Okay. So the description of this function is known to all parties. So this function depends on two inputs, x comma y. Now, unfortunately, Alice only gets x. Okay. And Bob only gets y. So Alice by herself cannot compute the output of the function. Bob by himself cannot compute the output of the function. So what they do instead is Alice, depending on her input x, sends a message mx to a referee. Bob sends a message ny to a referee. And the referee hasn't seen x comma y. I mean, if he had seen them, he would have computed. But referee is not supplied x comma y. But what referee instead sees are the messages mx and y. And from the messages, the referee will have to output his guess of f of x comma y. Okay, so the referee will output. So let us say some f hat. So the referee's function I will formalize by f hat. So referee will output f hat of mx, comma ny. Okay. Yeah, and the requirement is that okay, so the requirement is that with high probability, I mean, if you're talking for randomized computing, so with high probability, this output of the referee f hat should be equal to the correct output f. Okay. So this is the model. Is this clear? Okay. So for the case of equality, the referee gets some message mx and y, and then he outputs his best guess f hat, and f hat of mx comma ny should match equality. That means if x is equal to y, f hat should be equal to 1 with probability at least 1 minus epsilon. If x is not equal to y, this output f hat should be equal to 0 with probability at least 1 minus epsilon. Yeah. And think of Alice as having private coins. So this mapping from x to mx is a private coin algorithm. This mapping from y to ny is a private coin algorithm. If you want, you can even make the referee private coin. So so this function f hat, it's a randomized function. The referee uses private coins to compute it. And what we require is for each pair x comma y with probability. So now the source of the probability is only coming from the private points of Alice, Bob, and referee. So for each x comma y, the output of this procedure should equal the ideal function with probability at least one minus epsilon. Okay. So is this setting clear?
Yes.
Okay, so I think I have to take an urgent call. So just hang on. Who the hell is this? Signing in from some other device? Yeah, meanwhile, let me continue. Okay. Yeah. So let us look at the, okay. Just a Hello. Can you hear me? Sorry about that.
Yes.
Yeah. Yeah. Sorry. Yeah. I mean, today's a bad day. Shayantan just dislocated his shoulder. Okay. So he was calling from the hospital. It's really bad. I mean, 1 hour back, 10:30, he had to give a talk. And little before that, he said, look, my shoulder is very bad. Why don't you give the talk instead? And then now he called up with the latest report and all. Turns out he has dislocated his shoulder. So, and he's in a mess. Anyway, yeah. Sorry about that. But we have to do our work. Are you staying in on campus, education? No?
Yes.
Okay, good. Yeah, you have a support system. He has to move out of campus. So he doesn't have a support system. Yeah. Okay. Let's continue. So, is this model clear? The simultaneous message passing model? Yeah.
Yes.
Yeah. Okay. So, yeah, let's continue the equality example. Right. So, let us look at trivial protocol for this. So, trivial protocol is mx equal to x. So, Alice just sends all of x as a message. Bob sends all of y to as his message to the referee. Then the referee, of course, knows x, y, and can answer correctly. Okay, so he can compute f of x, comma, and all. So any simultaneous protocol has a simultaneous problem has a trivial protocol where mx equal to x and ny equal to y. Just Alice Bob sends the whole. So the challenge here is to come up with more efficient protocols. Can Alice use shorter messages? Can Bob use shorter messages? Okay, then the trivial upper bounds of n, comma n. So for equality, yeah, the trivial protocol is always there. The question is, can you do better? So let's first argue that if you are talking of deterministic algorithms, you cannot do better. So let's see. So let's see why that is the case. So let me write down what I'm saying. Okay. So why is that? So let's
Oh, so sorry. So joint level EQ is equality.
correct. Yeah. Yeah. So this is the simultaneous message passing model, which I've just
No, please go ahead. I
yeah,
know the
this is
model.
the model, so you can make sense of it. So Alice, Bob, okay, there's a referee. They send messages, and the referee has to output his guess of this function. So they have to compute this underlying function. This is equality. So first, we are trying to prove a lower bound of n plus n for deterministic algorithms. So let us say Alice uses less than n bits of message, deterministic algorithm. So this means that right. So suppose Alice uses less than n bits of message. So what does this mean? This means that there are two different inputs, x comma x prime, for which Alice has sent the same message, right? So now such that okay, yeah, and so let's see what is the problem with this. Okay, so now let us see what the protocol would behave when Bob is given the input y equal to x. So fine. So okay, so what is the strategy? We want to show the lower bound, so we'll argue by contradiction. So Alice is giving the same message for X and X prime. Let us say I fix Alice's input to X, Bob's input to X. Then this referee out here, so this referee should output 1. Okay. So in a deterministic protocol, we want, the answers have to be correct with probability 1. Like even referee is deterministic. So either the answer is correct or wrong for X comma Y. So we want the answer to be correct for every pair, X comma. Yeah. So there's no 1 minus epsilon business. It's either 1 or 0. Okay. So consider what happens when Alice gets X, Bob gets X. Referee should output 1. Consider what happens when Alice gets X prime, Bob gets X. Okay. So let me make this clear.
So that's just a proof, right? That in these two cases, you have the same message and referee cannot distinguish between the two cases. That's the proof, right?
Yeah. So case 1 is Alice gets X, Bob gets X. Case 2, Alice gets X prime, but Bob still gets X. Now, remember the messages are the same in both cases. So the because mx is equal to mx prime, so the referee will answer the same way in both cases. But this is a contradiction because in the first case, the Alice referee should answer equal. In the second case, the referee should answer not equal. Okay, but that is impossible because the referee is seeing the same scenario of messages in both. So this is the contradiction. Is this clear? Very simple. Okay, is this clear to everybody? Yeah. Hari?
Yes.
Yeah. Okay. So very simple. So this shows that Alice cannot use less than n. Similarly, Bob cannot use less than n. So we have proved n plus n lower bound, and it's also the trivial outcome. Now let us see what happens for randomized algorithms. Okay. So now we will talk of. So how will we create the next page? Okay. How do you create the next page out here? Shanta, do you know how to create the next page?
Yeah. So go down.
Yeah, I've gone down.
You have to do a plus, this plus thing.
I don't see a plus here. That's the problem.
Oh, I think what has happened is that since you're just write page 25 or something. Just change the page number. I think it will automatically generate it.
No,
it's not doing that.
No, it's not doing. Okay, so let me see if something automatically happens.
How are you getting this typed out? This should not be true. Usually that plus is how I make new pages.
Yeah, unsaved document. Rule with vertical line. That's strange.
There is a page plus on the top. I think that
this plus is grayed out.
No, the on
this
the
is
top,
zooming in.
on the.
Yeah. That's right. So there's a page plus at the top. So it's the second row.
Green
second
plus.
row. No. That's the third row. Just the row above it. And go towards the right. A page with a green plus as subscript. No, just before that. Yes.
Insert page.
Yeah.
Great. Yes. Okay. Thanks. Okay. So now we'll study what happens for private coin algorithm. Okay. So remember what we are doing is again recall equality in simultaneous message model. Okay, but yeah, before I maybe since Hari may not have seen this before. So okay, so as I said, the original motivation of Yao to introduce this was lower bounds of VLSI circuit. So the idea being the following: like how do you prove circuit lower bounds for VLSI? He said take the chip and divide the chip into two parts, the left part and the right part. Now let us say the aim of the chip is to compute the equality. So Yao said that let us say, so of course, if you have to compute equality, two inputs have to come in, but two inputs cannot come in the same place, they have to come in different places. So let us say the input X comes into the left of the chip, input Y comes into the right of the chip. So Yao said, divide the chip into two parts, okay, left and right. So there is circuitry in the left part, there is circuitry in the right part. But some information has to be computed from the left part to the right part, and some has to go from the right part to the left. So if you want to prove lower bounds on the number of gates or the amount of wiring, so abstract this out, okay? So ignore the complexity of the internal computation. So I'm not going to care how much circuitry I have in the left part or how much circuitry I have in the right part. What I'm going to care about is the number of wires that are going from left to right and from right to left. Okay. And now, if you consider this abstract problem and if you can prove a lower bound on the communication complexity, okay, then you have proved a lower bound on the number of wires. So this is how Yao proved lower bound on the complexity of VLSI, okay, on the number of wires. So is this clear? Okay, this is very rough motivation. Yeah. So yeah, so it's very useful to prove lower bounds in the limited computational models. Now let us see if private coin algorithms, so Alice can be private coin, Bob can be private coin, referee can be private coin. Let us see if private coin algorithms can do better for equality. So the answer is yes. Okay, so can do EQ with square root n plus square root. Amazing. Okay. And what is even more amazing is, yeah, I'm going to tell you how to do it. Okay. So what is even more amazing is the amount of time that went before this came out. So Yao proposed his model, and he in fact proposed this exact problem, equality in the simultaneous model. He asked this question, like, what is a lower bound for it? Okay, and the deterministic, of course, was easy to prove. He observed that and he said, what happens for randomized? And he asked the lower bound, and the first breakthrough that you can do better than n plus n came in 1996. Okay, so let us see how this is done. Yeah, anybody has any question or comment on this?
I don't have a question, but I have a comment
Huh.
about not about private coins, but I just thought this up. So I can't see it in terms of private coin yet, but if you give me a public coin, then I can definitely tell you a protocol right now. So if you
Okay,
have
so give me a public coin protocol.
yeah,
Fine.
so suppose you have an n bit public coin, okay? Then what both parties do is take
Right.
yeah. So you have an n bit public coin, and both parties essentially what they do is they take the inner product mod 2 with their inputs, okay, and whatever bit they get, that is what they send to the referee, and the referee just checks the bits. If the two bits are equal, referee says that okay, this is correct, and if the two bits are not equal, the referee says that okay, this is not correct.
Yeah.
That's
So
it, right?
yeah, that's it. So Hari, did you get that? So what
Yes.
Shantan is saying is this. So this is Alice Bob, and so this is the referee with all the three boxes. So now this is A, this is B, this is R. So there is this public coin out here. So let's call it R. Okay. So R. Okay. So this is the public coin. It's chosen it's a random bit string of length. So what Shantan is saying is the messages are 1 bit from Alice to referee, from Bob to referee. Okay. Remember, Alice gets this X from outside. Bob gets this Y from outside. Okay. So let's go this. So what Alice sends is just the dot product. So this is the dot product treating of the n bit string as a bit vector. And addition and multiplication are done modulo 2, integers modulo 2. So this is x dot r, y dot r. So of course, if x is equal to y, these two bits will be the same. And the reference strategy is very simple. If this he looks at the messages that he receives, the two bits, and declares the output equal if the two bits are equal, and unequal if the two bits are unequal. That's it. Therefore, it is very, very simple. Okay. Now the point is, of course, if x is equal to y, this works. What happens if x is not equal to y? So if x is not equal to y, you can prove that with probability half, x dot r is not equal to y dot r. So let's write this down. X not equal to y, probability x dot r equal to so x dot r equal to y dot r. So this probability is equal to half, exactly equal. Okay. So with probability half, the two bits are different, and the referee will say unequal with probability half. Okay, how do you boost the probability? So it doesn't look very good. In one case, the probability is 1 of correct answer. In the other case, the probability is half of correct answer. So what
No, this is good for us, right? So this is one-sided errors, one-sided error. So therefore, we can repeat and
yeah. So I'm just saying. So what we'll do is that we'll take k independent copies of this public coin, R1, R2, Rk, each chosen IID and uniformly from all bit strings of length. And what Alice will send will be x dot r1, x dot r2, x dot r3, so on. Similarly, Bob will send y dot r1, y dot r2, y dot r3, and so on. And the referee will answer equal if and only if all the message bits from Alice end are equal to the corresponding message bits from Bob. So of course, if x is equal to y, referee will answer equal with probability 1. If x is not equal to y, remember, each coordinate will exhibit inequality with probability half. So the probability that the referee gives a wrong answer, that means the referee concludes equal, will be half to the power k, which is dropping exponentially. Okay, so that solves the problem. So in if I want the probability of error to be less than epsilon, so I just need log 1 over epsilon copies of r, IID copies of r. So the message length is no longer 1 bit, but it's log 1 over epsilon bits. So that's it. So if you think of epsilon as a small constant, you can do it with order 1 bits of communication. Okay. So, or more precisely, if you want epsilon error, you can do it with log 1 by epsilon plus log 1 by epsilon bits of communication. Okay, is this clear, everybody? So this problem becomes very simple with public coin. It's also not very hard to prove a matching lower bound. Okay. So really, the difficulty is in the private coin. And you can see how the public coin was imported here. Both Alice and Bob should see the same R. Okay. So this will not work if Alice tosses his own R, Bob tosses his own R prime. Then I mean R will not be equal to R prime with high probability. So this becomes nonsense. Okay. So this is a case where you can see a tremendous advantage of public coin. What happens for private coin? So that's why the problem was open for a long time. I mean, of course, all this realization that we have done so far was solved already at the time of Yao, but only in 1996 or so, Andrew Zambainis made the first break. Okay.
So I have a sort of look ahead kind of question. So isn't there a way to turn public coins into private coins with some extra login communication or something?
That with extra login commission, that does not work for the simultaneous one.
Okay.
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 But we'll have more to say about that. So yeah. So what Shantan is saying is that recall, if I to drive the probability of error down, I took k copies of the public coin. Okay. Now, actually, to drive the probability of error down to epsilon, I needed log 1 by epsilon copies of the public coin. So what he's saying is that if I want to drive the probability of error down to, let's say, 2 to the minus 2n or something like that, okay, exponential small in n, I only need, okay, so Yeah. So I only need something like n copies of the public coin. Okay. So yeah. Okay. So anyway, so I mean, you require a little bit of work to push that argument, but it turns out that you can amplify the probability of error by repeating the public coin, then do some little clever thing with Chernoff and so on, and you can show that ultimately you can reduce the number of bits of the public coin. So here the public coin already, even for one copy, is n bits. So that's actually too much. You can reduce the number of bits of the public coin to log n. And then what Shanti is saying, that once the public coin is log n, then why can't Alice toss those log n coins and send it along the first person? The point is, Alice can do that, but what about Bob? Even if Bob tosses log n coins with high probability, Bob's coins will not agree with that. So this strategy, what you said, Shantan, will not work for the simultaneous decoding model.
Yeah,
It will work,
got that, got that.
it will work for other models. So that's it. I mean, okay. Separately, one can ask, fine, I don't want to completely remove public coins or something, but can I come up with an explicit protocol? I mean, not some abstract thing coming from Chernoff. Can I come up with an explicit protocol where the public coin is only log n bits? The answer is yes, and it will actually help us with the understanding of the private coin protocol. So let's do that.
So I have a question. So
Yeah, go ahead.
so if they both of them toss square root of n coins, then they have a very high probability of having the same kind of outcome. So that's why this thing holds.
No.
No,
Square root
so
n and n.
if Alice and Bob independently toss square root and coins, sure. So I mean, you're talking of the birthday paradox, but they still don't know. I mean, which of those coins agreed, right? And so first of all, that's one problem. And remember, the number of
No,
coins.
Pranab, but this is not birthday paradox. Birthday paradox would be if the coins were n by 2, not square root n. Because it's the number of bits.
So the birthday paradox will be on the number of elements in the set. So remember, the number of elements in the set is 2 to the n. So maybe, I mean, if you can use your birthday paradox ideas and somehow push it through, it will still look like something like square root of 2 to the n. Okay. So this is square root of n. Okay. So you'll see what is that. It's not a birthday paradox, though. Yeah, I mean, the first sight one may think because it's square root. But yes, before we do the private coin, it will help you study the public coin and reduce the number of bits. So can reduce the number of public coin to log n. Okay. By a simple idea for, so for, I mean, this is only for equality. So the idea is as follows. So remember, Alice is getting X. So Alice encodes X using some error correcting code into a slightly larger string. So internally what Alice does is that she will create CX. It's internal computation. It's not revealed to any part. And Bob will similarly create CY. Okay. So they use the same error correcting code. Yeah. So we know there are error correcting codes. So if X is n bits, let us say CX will be something like 100 n bits. So they will expand the number of bits by a constant multiplicative factor. Okay? So similarly, Y is n bits, CY is something like 100 n bits. But what do I know? This error correcting code has constant distance. So constant distance means if I look at two different bit strings X and X prime, their encoded versions, CX and CX prime, will differ, let's say, in 1% of the locations. Okay, so 1% of 100 n bits, so they'll differ in about n bits, okay, out of 100 n bits. So similarly, if Y is not equal to Y prime, CY will differ from CY prime in about n bits out of 100 n bits. So there are such error correcting codes known in the literature. Okay, we're not going to prove it now. We are just going to accept this fact.
I just have a question. So here, do we need a? You're saying that the distance of the code is small.
Distance of the code is not small. It's a constant. Right?
It's a constant. So so these are bad codes. I mean,
I mean, how much distance do you want? Come on.
And from the coding theory point of view, this is not a good code, right? I mean, you want the distance between the code words to, oh, I see. No, what I'm
This
saying
is
is
quite
complete
good
nonsense.
already. By the way, this is a non-trivial code to achieve.
No. What I'm saying does not make any sense. You want to reduce distance because you want to increase the number of code words. Right. Sorry. Yeah.
Yeah, so this is quite good. I mean, maybe you can go up to distance half and all with better codes, but yeah, even achieving this, expand n to 100n and get n locations different out of 100n is not an easy thing to do. Okay, yeah, I mean, anyway, you will see that. I mean, we can even for the purpose of this problem, we can do by with even lesser codes. But let us assume that there are codes of this kind. Now, in the cleverer protocol, so what we'll do is that the new R is a random location in code word. So in other words, R, okay, is a random number between 1 and 100. Okay. So in other words, the number of bits required to choose this R is only order log n bits. Okay, in fact, it's log n plus log 100. Yeah, so that's it. So now what happens is Alice internally encodes X into CX, Bob internally encodes Y into CY. Then they look at the public coin R, which is just prescribing a random location from 1 to 100. And Alice will send just the rth bit of CX, and Bob will send the rth bit of CY. So let me write it. So Alice will send CX, the rth bit, and Bob will send CY, just the rth bit. So back to 1 bit. And now the referee will answer equal if the 2 bits are equal. He will answer unequal, the 2 bits are unequal. Why does this work? Again, if x is equal to y, this will work with probability 1. If x is not equal to y, I know that the code word cx and cy differ in n out of 100 n locations. Okay. So with probability, okay, 1%, this public coin R will point to one such location. Okay? So the probability that the public coin R points to a different location is only 1%, 1 by 100. But with 1 by 100 probability, Alice gives the correct answer, not equal. Okay. But then you can amplify this probability. So now I don't like 1 by 100. I want probability. So the correctness probability is 1 by 100. So the error probability is 1 minus 1 by 100. The error probability is 0.9. Very bad. I want the error probability to be 0.001. So fine, repeat it a constant number of times. Okay. So again, if I want the error probability to be less than epsilon, choose like several random locations. So choose log 1 by epsilon random locations from the code word. So the amount of bits of public coin that are required will be log n times log 1 by epsilon. The error probability will be epsilon in all cases. X equal to y, error probability is 0. X not equal to y, error probability is at most epsilon. So is this clear? Okay. So
these random coins only need, so they're what, they're locations, right? The random coin R is giving you a location in the code.
Correct.
And that location is what you have to check. And to so that this is how you turn it into a as in,
well, this is still a public coin protocol because Alice and Bob need to look at the same random location.
Right, but you only need like log n bits to specify each location. And if you're repeating it a constant number of times, then Alice can just toss these.
No. So this is when we'll use the birthday paradox idea of Hari Krishna. So the number of values R can take is about 100n. Okay, so if Alice would take something like square root of that, so let's say 10 times square root n random choice of R, Bob takes 10 times square root n random choices of R, but independently.
Then with high probability they don't collide. Actually,
no, they will collide somewhere.
With constant probability they don't collide.
With constant probability they'll collide somewhere. Okay.
Less than square root n, right? Less than square root n or more than square root n.
No. You need about square root n. So square root.
No. why I'm asking, see, about this state, this word about, there's a problem here because there is a threshold phenomenon. You go even slightly below square root.
Yeah. So no, I want correctness. So I have to go above 10 times square root.
You have to go. Okay.
Yeah. So let us say, okay. So I mean, instead of 10 times square root of n, let us say I go to 1,000 times square root. Okay. So Alice tosses 1,000 times square root of n locations. Bob tosses independently 1,000 times square root of n location. Then those two sets will have a non-trivial intersection probability, something like more than 99%.
Oh, yeah.
Okay. But then what is the message that Alice has to send? Alice will have to send the entries at those locations as well as the locations themselves. Okay. Because there is no consistency in locations. So Bob will also have to send the entries at those locations as well as those locations. Then the referee will see, okay, what are the locations Alice has probed? What are the locations Bob has probed? Is there a common location they have probed? So 19% chance you will find that there's a common location they have probed. And then you look at what is the bit of Alice at that location, what is the bit of Bob at that location, and then you'll answer accordingly. Okay. So this protocol will work, and then you can further amplify it. Okay. So is this clear?
But now I think you should write things down because we have been talking in the
No,
air for longer.
yeah. So I'll write it down, and I mean slides that I'll put up will not be this. So
Okay. So just to get things clear, this was like, I mean, I'm just going to repeat it very slowly. So Alice and Bob cannot communicate. Therefore, Alice cannot toss her own coins and send it to Bob. That is clear. So how do we start? So this is like a more sophisticated version of the dot product mod 2 idea. So what do they do? There is some code which has very good distance properties in the sense that if you have an n long bit string, that code maps it to a space which is 100 n long. And this code is known to both Alice and Bob before the protocol starts. Great. So when the protocol starts, Alice gets X, Bob gets Y, and each of them encode these into code word CXCY. Okay. Now the protocol is just this, that suppose you had a public coin. That public coin would be in a log n, an order log n long public coin. That is, it's in like box 100n. And why? Because that public coin is essentially it's a pointer. It points to a location in the code word. So what do Alice and Bob do? They look at that location, look at the bit in that location, and send it to the referee, and referee just compares and says that okay. So if they're equal, I'll say equal. If they're not equal, I'll say not equal. Okay. So if X and Y are equal, then with probability 1, this protocol is always correct. If X and Y are not equal, then the probability that these two are correct is something like 1 over 100. That is n over 100n, which is 1 over 100. Which is slightly worse than the half that we were getting earlier, but fine. You can boost it by taking many random samples, many ID samples of the public coin. Okay. But now our aim is to sort of reduce, not use the public coin. So how do we do that? We use the birthday paradox idea. So the birthday paradox idea says that if Alice and Bob individually toss independent coins, as a sample independently from the set box 100n, and and they sample slightly more than square root 100n number of samples.
Yeah.
Then with very high probability there will be a collision, that is, there will be a common element in the samples that both of these guys produced. So Alice and Bob essentially send this list of list of coins that they have sampled to the referee separately. There is no public coin anymore, to the referee separately, and they also send the bits corresponding to these things. And the total amount of communication is still very much order log n, right?
Well, so the complexity of communication is square root of n times log n.
Square root n times log n. Square root n times log n.
So, but this is now a bona fide private coin protocol. And I mean, you can amplify it. I mean, it works with probability of error at most epsilon after amplification. So So the complexity is square root of n times log n, because to send each location you need log n. Okay. So we are almost there to what Ambine has achieved, but you observe that there is no log n out here. Okay, so Ambine did even better than this. And now we are going to see how, but yeah, but we have already made some progress, and as I said, we'll further develop these ideas. So is this part clear, Hari?
Yes.
Yeah. So we can come down to this square root of n times log. So now I have to even throw away the log. So what the private kernel algorithm does is, actually, I don't know what Ambine really did, but I suspect what he did must be very close to this.
Can I make a guess?
Yeah.
So can we de-randomize the choices of R? Then maybe we
No.
would be.
No, not really. Okay, so let us see what. So I have drawn. Okay, I've drawn some square. So what is this? So let me write down. So I'm just describing Alice's operation. Bob will do the same. So this square, okay, is so I should say what are dimensions of the square. So dimensions are 10 times square root n times the same 10 times square root n. So the total number of so here's an array with number of rows 10 times square root of n, number of columns 10 times square root of n. So the total number of locations is 100 times. So remember, the number of bits in my code word is 100 times. But instead of thinking of the code word as one long string, I rearrange a long string into a matrix. Okay. So the string of length 100n has been rearranged in any fashion you want, let's say row major fashion, into a 10 square root of n times 10 square root of n matrix. So this is how it's rearranged. Now Bob also does the same thing. He computes his code word cy, but rearranges it into a matrix like this. Now what Alice sends to the referee is a random row of this matrix. So let us say this is row number I.
No, sorry, I'm not clear on this. How did you get the matrix?
Just take the code word, but instead of writing the bit string as a long vector, write it as a matrix.
Is there some rule which says where to break?
No,
it?
nothing. I mean, you choose your way of converting a long vector into a matrix. I mean, let's say row major form, whatever.
Oh, okay, got it.
Okay. I mean, both Alice and Bob will have to use the same rule, but that's about it. You can choose your favorite rule to rearrange a vector into a matrix. Okay. So, so this is what Alice does. So she computes Cx, but writes it as a 10 square root of n times 10 square root of n matrix. Then she chooses a random row I and sends the index I as well as the entire contents of the row to the referee. And now you can sort of guess what Bob will do. Bob has this cy out here. Okay. Bob chooses a random column and okay, so let us say column number j, and to the referee, Bob sends the index j, so he sends the column index as well as the entire contents of the column. Okay. So now what is the referee is getting? The referee is getting a random row from Alice and a random column from Bob. Now whatever row and column are there, they intersect in exactly one element. So let's say they intersect, for this case, in this element. Okay. And that will be this. And the referee also knows, I mean, it is the ith row and the jth column. So he'll just look at the element I comma j out there. Okay, so you look at I comma j from Bob's message. You look at I comma j from Alice's message. Okay, and then he'll check whether those two bits are equal or not. That's if they're equal, answer 1. If they're unequal, answer 0. This is the referee's protocol. So why does this work? So first, before why it works, let us see the complexity. So the message length of Alice consists of the index I, so that is log n, and the entire contents of the row, but the row is only square root of it. So now the complexity becomes square root n plus log, which is still order square root. Same for Bob. Like there is log n for the column index j plus square root of n for the entire contents of the column. Okay. Now the point is, Alice has taken a random row, Bob has taken a random column. So this index I comma j is a random element out of those random location out of those 100 n. Okay. So essentially what the referee is doing, referee is checking what is the content of a random location of Alice's code word, what is the content of a random location of Bob's code word, and is checking whether they're equal or not. So we just use the error correcting property, and if x is not equal to y, the referee will control not equal with probability 1 by 100. Okay, and then you go and amplify it. So is this clear?
I mean, it's essentially the same thing. I mean, okay. So here's what I want to say. So it's sort of like that. I mean, what do you do to get rid of the log n thing, right? You want to sort of get rid of this. You want to come up with a scheme which automatically tells you where to look. Okay. So in the public coin protocol, R was telling you where to look. And in this protocol, just this idea that you can arrange it in a matrix, and you just have to ensure that one element is common. That was what was being ensured by the birthday paradox previously, but here it is being forced just by the fact that things are arranged in matrix form. So you need not share any public coin or any such thing anymore, right?
Yeah. So here the fact that there is one, in fact, there's exactly one element in common, the way the things work out.
So that is exactly why I said, why can't we, instead of picking public coins like this, why can't we pick public coins like, say, by walking on an expander or something like that? Then just one of these guys can.
Well, I mean, how do you ensure consistency? That's the whole point. How I mean, at some point, I mean, the referee is only interested in the same bit, right? That is consistent. So here the consistency gets forced. I mean, whatever I is, whatever j is, they will have to intersect in exactly one branch.
Okay.
So the only thing that I want is that the intersection should be a random location, but that is also arranged beautifully by taking I randomly and j randomly. So it's a very specialized thing for equality. Just a neat clever idea. The paper is, I think, only 3 pages. Yeah.
So that's a beautiful idea.
Yeah. Actually, I don't know if this is the idea in the paper, but I would suspect this is. Okay. I've never read that paper. So, yeah. So that's it. So we can do with square root of n plus square root. Okay. Any questions, Hari? No? Is this clear? Yeah. Okay. So now we are done. Square root of n. Now the question comes about lower bounds. So after this came out, then people got down and said, "Oh, amazing protocol," and they tried to prove lower bounds. And then within a couple of years, lower bounds came out, which showed that square root of n is tight. Okay, so there was a paper, I think Nissan and Segedi 1 year later, and then there was a more general lower bound proved, and with a slightly simpler proof by Baba and Kimmel. But anyway, so they proved that for equality, the square root of n lower bound for private coin algorithms is tight. So now we'll prove that, but we will not prove it with the original technique. The original technique is for combinatorial, so we'll prove it beautifully using information flow. Okay. And this proof again is very recent. It's a 2015 result. So look at the amount of time gap that has gone in getting the deep understandings of this problem. So this is a paper by basically Singapore people like Hartmut Klauk and Botesh and Dmitry Gavinsky. So let's go ahead. We'll try to prove the square root and go up using information. So this is the shortest proof that I know of the square root and go about. The earlier proofs were, I mean, all quite hard. Okay. So what is the idea? Okay, so consider the uniform distribution on the bit string. So so this is the uniform distribution on the inputs that I'm talking of. X is modeled by random variable X. So X basically refers to the input space. And now we ask, okay, so I can talk of MX. So MX is the random variable of Alice's message, and NY is the random variable of Bob's message. Right. So yeah, so MX, NY. So when I talk of MX, NY, what where is this randomness coming from? The randomness is coming from actually for the proof we look at MX comma NX. So what do I mean by that? So these are not independent random variables that I'm considering. So choose a uniform bit string of length n and supply the same bit string to Alice and Bob. So we know that the protocol has to output equality with probability 1 minus epsilon for this. And now for this input setting.
Sorry, sorry, Pranav, can you just repeat that last bit? I missed it.
So I'm saying consider the following thought experiment. So choose a uniform bit string of length. Okay, that is modeled by the random variable X. Supply the same bit string to Alice and Bob. Okay, so then the protocol has to answer equal with probability at least 1 minus epsilon, right? The private key protocol. Now, Alice, so now I look at the random variable describing Alice's message. So the randomness here is coming from the random choice of X as well as the internal randomness of Alice. And similarly, I can talk of the random variable nx. So the randomness is coming from X as well as the internal randomness of Bob. But remember, these are correlated random variables because both are getting the same X. Even though the private coins of Alice and Bob are independent, the inputs that I'm putting here are the same X. So these are correlated random variables. Okay. So are the definitions clear? Mx, comma nx. So I'm going to study these random variables. Okay. In fact, I'm going to study something more. I'm going to take mx and n1 x. So I'm going to study what happens. Okay. So remember the same X is fed to Alice and Bob. So Alice outputs a message, which is MX. Bob would output NX, but now what we do is we make Bob output T independent copies of the message. So where is the independence coming from? They use the same X, but Bob independently tosses his private coins for N1, for N2, up to N. So that is the setting I'm talking about. So now these T plus 1 random variables, they're jointly distributed because they get the same X. Then, but what do I know? I know that the private coin of Alice here is independent of the private coin of Bob. And even within Bob, he uses independent private coins for N1, N2, N3, and so on. So that's the joint distribution that I'm going to consider for the proof. Okay, this is a lower one proof. So I'm going to consider this random variable. So the protocol defines this joint random variable, and we're going to analyze this information theory properties. Clear so far? The setup? Okay. So now, so let us say Alice's message. So let's fix one more thing. Like Alice's message is A bits, and Bob's message equal to B bits. So we have some private coin protocol with A bits and B bits. So now what I'm going to do is, so I can say that A is larger than okay. So So the first step in the lower bound proof will be this observation. Consider the mutual information, Shannon mutual information between mx, okay, and the remaining variable. Now, of course, this mutual information is upper bounded by the entropy of mx, but remember mx is supported on a bits, so the entropy is at most a. This shows that a is greater than or equal to this mutual information. Then I'm going to write this mutual information by the chain. Okay, so some I will be the mutual information between mx and ni x conditioned on the prefix n1 x I length x. So moving this out. How do you move this out here?
Which one? The text thing.
Yeah.
So I think you have to select it first.
Okay. Anyway, I suppose it's clear enough. We have written everything out here. So, or maybe I just break it up. Right? So,
Yeah, see, now it's selected. Yeah, now it's selected. Now I think we will be able to grab it.
okay. Anyway, let me just break. So this mutual information is equal to, by the chain rule, sum I equal to 150. So what is the ith term here? Is the mutual information between mx and the ith random variable here, which is ni. Okay, condition on n1 to ni minus. So far clear, everybody? Okay. So what do I get? I get that there exists an I. Okay, so what does this? So this implies.
I just have a comment here.
Hmm.
So does this conditioning not simply not reduce to conditioning on x?
What? X.
Yes, I mean I'm saying you can replace the conditioning on n1x, n2x up to ni minus 1x on just the conditioning on x.
Yes, we'll do that. We'll do it. So there exists, let us say, I naught, okay, where this mutual information is small. Small means it's smaller than the average. So the mutual information between mx and ni, x conditioned on n1 x. This is less than a by t. Okay. So this implies that there exists some I index I naught where this mutual information term, condition mutual information term, is less than a by t. Okay. So what is this telling us? So this tells us. So let me write it down. So remember the conditional.
Wait, let me just get this straight for 1 second because I'm a little woozy. So you upper bounded the large mutual information term by the entropy, which is a bits. That's because it's Alice's message. And then you divide it by t because there are t terms, and that gives you the uniform average. And then you're just saying that there exists one guy who is less than equal to average. Okay, fine.
Yeah. So I'm going to write the conditional mutual information as an expectation. So the entropy of so this mutual information, this is a quotient term. M X mx colon I naught x condition. Okay. So what I want to fix out here, so in this expectation, I want to fix the I minus one messages of Bob to something. Okay, so I'll just call it N1 to N I naught minus one. So this expectation is less than A divided by E. Okay. So yeah, this is I naught. Okay, so what I've done, so I've just gone to the same I naught and I am making sense of the conditional mutual information. So the conditioning was on the messages of Bob, the first I naught minus one messages of Bob. So I'm just taking expectation over all possible values of the first I naught minus one messages. So let's say I fix the first I naught minus one messages, call them N1, N2 up to N I naught minus one. After fixing it, I get a conditioned distribution on my random variables, and now I'm taking the mutual information between. So this is less than A by T, just equivalent to this. So is this clear so far? Okay. Now let's see what to do. Yeah. Now, so this is an expectation. So this means that there is a setting of the first I naught minus one messages of Bob to some suitable values, so that the mutual information between mx and ni0x arising after this setting is less than A by T. Okay, so yeah. So what have I got? So this means that there exists N1 and I0 minus 1. Okay, so these are the messages such that the mutual information between mx and I0 x conditioned on N1 and I0 minus 1 is less than A by T. Okay. So far, so good. What does this do? Okay, so I fixed the first I0 minus 1 message of Bob. So this means that I'm lowering the entropy of the input random variable x. Okay, so earlier the entropy of x was, so let me write, so earlier hx was n. Okay, but after fixing n1 to n I0 minus 1, okay, so that will affect the probability distribution x also. So what can I say? I can say that h of x goes down, but it doesn't go down that much. It is greater than or equal to n minus. So how much I have fixed? I have fixed the first I0 minus 1 messages. So I0 can be at most t. So t, and how many bits for one message? Remember, these are Bob's messages, so they're b bits. So it becomes n minus t. So after fixing these messages of Bob, there is still a lot of entropy left in the input random variable x. It is greater than n minus t. So now, what is this telling me? So the, let us say the rows I label by Alice's input, and the columns are labeled by Bob's input. So I'm setting up a different matrix. So this is called the communication matrix. And what is the probability distribution analysis inputs that I put? I put the distribution on X after fixing these guys. Okay? So this is X after fixing, but there is still enough entropy out here. So there are actually many such. I mean, I want to say that the number of bit strings that are X that are consistent with this fixing is quite a lot. Okay? And similarly, for Bob also, the number of bit strings that are consistent are quite a lot. So let me draw what I mean. So there's quite a lot of entropy out here. So there's quite a lot of variation possible out here, and similarly, quite a lot of variation possible out here. Now what do I know? I know that even if I choose an X after this fixing, so even if I choose the input consistent with this fixing from here, so Alice's message is this random variable mx after the fixing. Bob's message is ni0x after this fixing. So the mutual information between them is small. It is less than a by t. So in other words, what is this telling me? So this you can now make formal by Pilsker. So Alice's message for like x, okay, consistent is close to Bob's message for x consistent with fixing. Remember, these are private coin protocols. So, so the action of Alice, like Alice is fed an X from the random variable capital X after fixing. Okay, so Alice is fed a message from here, but once she is fed the message, also once she is fed the input X, her message MX, okay, is controlled by her private coins, which are independent of Bob. So, like similarly, when Bob is given the input X, his message Ni0A of X depends only on his private coins, which are independent of that. So far, so good. But now what I'll do is that I'll consider the scenario what happens when, okay, look at two different inputs, X and X prime, coming from this distribution after fixing. And for Bob's input, just look at X. Now Alice's message for X and X prime, okay? Yeah. Oh, actually, I should also say X prime. So what do I know? I know that the Alice's message for X and X, Alice's message for X and Bob's message for X, okay, are close to each other. The probability distribution because the mutual information is small. So that is principle. So what I want to say is that these are close to each other. So similarly, Alice's message for X prime and Bob's message for X prime are close to each other. Okay. Similarly, from here, like you put the same X prime here, same X prime here, they're close to each other. Okay. But now I ask, what happens if some adversary puts X as input to Alice and X prime as input to Bob? Then remember, like X and X prime are coming consistent with distribution. So this means that Alice's message for X remains the same as before. Okay, Bob's message X prime remains the same as before, but they're all close to each other. Okay, so that means if the protocol answered equal for X comma X, X prime comma X, the protocol is forced to answer the same thing equal for X comma X prime. But that is wrong because X is not equal to X prime. So what I'm saying is that once I have cut down to this subset of messages, which are consistent after fixing, there is still enough messages in this subset, okay, enough juice in this subset. Now, you take an arbitrary message from this subset, okay, feed the same message X here, feed the same message X here, the resulting message of Alice and Bob are close. But so this will hold for X comma X, X prime comma X prime. But Now the action of Alice, the message of Alice only depends upon her input X. So if the adversary would put X for Alice and X prime for Bob, Alice will still output this message. But now the point is that this message X of Alice is close to the message X prime of Alice, which is close to the message X prime for Bob. But now the referee is getting the same pair of messages, whether the input is XX or whether the input is XX prime. So how can the referee answer differently? This gives the contradiction. So this gives the contradiction when the following things happen. So let us. So what do I want? I want for this contradiction to occur. As I said, the mutual information is less than a by 2. So that means that the messages are the same. So we'll use Pinsker here on this. Okay. So Pinsker. So what is Pinsker telling us? Pinsker implies that mx is approximately equal to average m, okay, within, okay. So what is L1 distance within L1 distance of square root a by 2. Okay. So this message mx is close to the average m. In other words, this message mx is close to a fixed probability distribution n. Similarly, mx prime is close to the fixed probability distribution n. In other words, Alice's message is almost the same for x and x prime. Similarly, Bob's message is almost the same for x and x prime. So that gives a contradiction. What happens if Alice gets x and Bob gets x prime? So what do we want? We want square root of a by t to be small. So t has to be reasonably larger than a. And right. So let us say t equal to 100a. Okay. And what we want is that there is enough juice out here after the fixing, so n has to be larger than this. So let us say n is larger than 10 times TB, okay, which means it is 1000 AB. So what have I proved? That the product AB is less than n. In other words, if I now want to balance the message lengths, this says that A has to be less than some square root of n divided by square root of 1000. So, guys, for A equal to B, A is less than square root. So that finishes it. Questions? Yeah. Okay. Hard to believe there are no questions. I mean, this is a very clever part of the argument. Okay. So Hari, is that clear to you?
Yes, kind of.
Okay. Yeah. Fully. The slides will be even nicer, and yeah. So I'll put up I'll put up better slides, and I mean I'll put up this video for now, but I'll probably replace it with a more polished video with the slides later. Yeah. So we'll stop here today, and in the next lecture we will study what happens if we have to do not one copy of equality. We have to do not one copy of equality, but k independent copies of equality. So Alice is given x1, x2, xk. Bob is given y1, y2, yk, and the referee has to output for each location I whether xi equal to yi. So the output of the referee will not be a single bit, but it will be k bits, whether equal or not equal for first location, equal or not equal for second location. So, and we'll see that, I mean, naive arguments would say that, so we want to prove a lower bound on the communication complexity. So of course, you can repeat the same protocol k times. So k times square root of n will be the upper bound. Okay, in fact, yeah, k maybe even slightly larger. K times square root of n will be the upper bound. The question is, can you prove a matching lower bound? And we'll see how information theory will allow us to prove a matching lower bound for that. And again, this took a long time to come out. So this came out only in 2001. So the naive techniques would prove a lower bound of square root of k times square root of n. But we'll see how information theory and the only way to prove the optimal bound is information theory. We'll see how what we have already seen in this course will help us to prove the optimal lower bound of k times square root. Okay, so this is called a direct sum problem. It means that if you want to solve k independent copies of the problem, do you require k times the amount of resources? So at least for equality under this model, it turns out that you do need k times the amount of resources. It's not, I mean, it does not hold for all problems, but for this problem, the direct sum property holds. Okay, I'll stop now. I'll see you on Thursday.